Hey everyone, and welcome back to PrepFusion. I'm Anish, and today we'll be starting the lecture 5 of engineering mathematics, which is from the linear algebra chapter. Today we'll learn many different, also new types of matrices. We already learned few types of matrices. In this lecture, we'll also learn many more different types of matrices, which will be helpful about by knowing their properties. We can also solve few questions, okay, gate questions. I will solve those in the next lecture. But before starting the new types of matrices, we have to obviously solve the questions that I gave you as a homework in the previous lecture. So this was the first question where we have been given a matrix A, okay, and we have been given the matrix B, and we have to find the determinant of adjoint of A, determinant of adjoint of A, determinant of adjoint of A, okay, and then determinant of adjoint of B, determinant of adjoint of B, and determinant of adjoint of B. Okay, so how do we solve this? So whenever there is a relationship given between the B and A, obviously you can simply use that determinant property, okay, that I will tell you. But let us first find the determinant of this, and through that we can simply find the determinant of adjoint of A. What will be the determinant of adjoint of A? It will be equals to the determinant of A raised to the power n minus 1, where n is 3 in our case, because the order of this matrix is 3. Okay, so first we have to find determinant of A. So what will be determinant of A? So what I can do is I can simply use what do you say, simple simultaneous operations, okay, because I have a 1 over here, I want to make these two 0. So what I will do, I will change my row 2 to row 2 minus 5 row 1 and row 3 to row 3 plus 2 row 1, okay, plus 2 row 1, row 3 plus 2 row 1. Now this is the case. So what will the matrix become? So this will be 1 3 2, this will be 1 3 2, and this is like we are subtracting with 5 with this, so minus 5, right? Minus 5, so this will become 0 obviously, and this will also become 0, but we are subtracting 6 from we're subtracting 15 from 6, so this will be minus 9, okay, minus 9, and then we're subtracting 2, we're subtracting 10 from 2, so this will be minus 8. We're subtracting now, for third row, this is we're subtracting 6 from this, so this will be 2 only, okay. So no, okay, we're adding with this, so this will be what, 6 plus 8, which is 14, okay, and we're adding 4 with this, so this will be 13, and we'll find the determinant of this. So it will be simply equals to 1 into minus 9 into 13 plus 8 into 14, okay. So what is 13 into 10? 13 into 10 is 130, so it will be simply 117 minus 117, and this will be what, this is like 14 into 10 is 140, and we have to subtract 28 from that, so it will be 132 and 20 112, okay. So this comes out to be minus 5. So our determinant of A equals to minus 5. Now what will be the determinant of B? Like we know this relationship, that is B equals to 3A, right? This is the relationship that we have. Now what will be the determinant of B? It will be 3 raised to power 3 into determinant of A, right? Because order is 3, so it will be 3 raised to power 3, right? So this will be 27 into minus 5, okay, and it will be around 100 and 135, minus 135, okay. This is actually quite a lot, okay. So like now let's solve the questions. So First question is determinant of adjoint of 8. Let's solve them one by one. So let me just copy this. Still, let me do one thing. Can we do one thing? Like, this is too big of a number, right? 27 is too like big of a number. I can change the question because, okay, let's not change this because some of you may have solved it and you may have gotten upset. Like, this is just a big number and we'll just get a very big number. That is the main thing, but that's fine. So here, what will be determinant of adjoint of 8? It will be simply equals to n minus 1, determinant of a into n minus 1. So this is a formula that we just derived in the previous lecture. So what is determinant of a? It is minus 5 raised to power n minus 1, which is 3 minus 1, which is 25. Okay, which is 25, right? Now what is adjoint of a? Determinant of adjoint of a, it is the formula of determinant of a n minus 1 minus 5 raised to power whole square. So this is minus 5 raised to power 4, which is equals to 625. Okay, and what will be my determinant of adjoint of a? It will be determinant of a n minus 1 whole cube. Okay, so it is, if it is n minus 1 whole cube, it is simply like minus 5 raised to the power 2 raised to the power cube, which is 8. Okay, which is a quite big of a number. So what is it actually? It is let me use the calculator. Just hold on a second. So it is like 5 raised to power 8. Okay, this is quite a big number. Okay, let me keep it like this only. Okay, or let me write this. Let me keep the other numbers as big. I didn't expect those numbers to be that big. Okay, I just framed the question and just I put them as it is, but now I am realizing that like the number became quite big. Like, if the determinant was smaller, then it would have been an issue, but I should have thought it through. So what is determinant of adjoint of b? So basically it will be determinant of b into n minus 1. So it is basically like b, order of b will be same because they are almost like related with equal sign. So order of b and a are same. It is only multiplied by a scalar number. So it is also 3, order of this also 3. So here I should write n equals to order equals to 3. Okay, so yeah, now this is the case. Now basically determinant of b minus 1, this will be 3 minus 1. So like this will be 3 minus 1, which is determinant of b is equals to minus 135. So minus 135 whole square, which is equals to, this will be a big number actually, 18,225. Okay, now next is this determinant of adjoint of b. So this will be n minus 1 whole square. So this is like minus 135 raised to the 4. I won't solve it because this will be a very big number, which is of no use to us. Okay, and this is minus 135 whole raised to power 8. Okay, so this will be again 135 whole raised to power 8. Okay, so yeah, this is the case basically. So these are the solutions for this question. Now let's move on to the next question. So this question is very very interesting. I gave you as a homework that if x and y are non-zero square matrices, they are non-zero means they are not null matrices. If x times y equals to 0, basically a null matrix, then which of the following options is or are correct? Okay, you have to comment about determinant of x and y with the help of this relationship. So like in examination, if this question comes up, you will already know the answer and you will directly solve it. But here, as I have to prove few things, I will solve it slowly. Okay, so but in examination you don't prove things, like you can obviously when you don't like something new comes up. Okay, some similar type of this question comes up, but you totally don't know that, like you haven't previously solved it. But this one obviously I'm solving in front of you, so you know already the answer to this. Okay, but if you don't know, then obviously you have to go through this basic method. So you have to think that these are commenting about the options. You have no idea, right, where to start from. So you start from the options. So if they're telling that, let's check if this is possible or not. Determinant of x equals to 0 and determinant of y not equals to 0, if this is possible or not. So basically let's check option A. Okay, suppose, and let's check if it is like giving me a valid solution. Okay, if I assume that determinant of x equals to 0 and determinant of y is not equals to 0. So suppose simply that determinant of x equals to 0 and determinant of y is not equal to 0. Now if determinant of y is not equals to 0, okay, then what does that mean? That means that y is invertible, x is not invertible. So x is not invertible and y is invertible. Okay, so let me start with this relationship. So they are telling us that yeah, this is valid relationship, that x times y has to be equal to 0. This has to be valid. Okay, and so if this is valid, then let's start from this relationship. Okay, never start a relationship. Okay, so yeah, that's okay, that's okay. Only start if you have very time. Okay, else your brain will get damaged, trust me. Okay, xy equals to, just joking, xy equals to a null matrix, and now we know that y is invertible, x is not. So I can do y inverse. I can post multiply y inverse on both sides. So if I post multiply y inverse on both sides, this will be y inverse equals to null matrix times y inverse. Now anything multiplied with null matrix is the null matrix itself. Anything multiplied with 0 is 0 itself. So this, now this one will become y times y inverse is identity matrix xi equals to null matrix. Now obviously x times I is x itself, so x is equals to I. So here what do we see is that like x is equals to null by this relationship, but in the question they have told us that x and y are non-zero square matrices, but x and y are, like it may so happen that even though it is non-zero, the determinant can be 0 if the two rows are same or two columns are same. It is non-zero matrix, but still determinant is 0. Okay, but here this is directly telling me that x is a null matrix. Not possible, but x is not equals to null matrix and y is not equals to null matrix. Okay, hence this is contradiction to whatever the statement the question has told us. So obviously a can't be a isn't a possible solution. Okay, a isn't a possible solution. So let's check for the b option. In b they are talking about this, one is 0 and one is non-zero. Again same thing will happen, we'll see. This time y will be equals to the null matrix. So x is not equal to 0, determinant of x is not equal to 0, determinant of y is equal to 0. That means one is invertible, one is not invertible. So this time our x will be invertible, okay, and y won't be invertible. y not invertible. And like we'll apply the same thing only. Okay, but this time what we'll do, like we know the relationship that x times y is a null matrix. Okay, now what we'll do, we'll multiply x, pre-multiply x inverse. So if I pre-multiply x inverse, what will happen? X inverse x y equals to pre-multiply, right? So this is x inverse 0. So this will be iy 0. Okay, so y is 0. Again, this is a contradiction because we assume that x and y are non-zero matrices. Okay, so this is a contradiction. So again, b also won't be a possible solution, possible option. So b is also gone. So let's go for the c option. So c option, they're telling that determinant both of them are equal to 0. So if the determinant of both of them are equal to 0, let's keep this option. Let's first go for this option. Again, for this option, right, like it's the same thing only. Determinant of both of them are non-zero. So determinant of both of them are non-zero. Okay, if determinant of both of them are non-zero, just hold on a second. Yeah, determinant of both of them are non-zero. That means both of them are invertible. Both of them are invertible. Sorry for the sudden pause. Y is invertible. I was just thinking about someone else. Y is invertible. So here, like we will use the same relationship, right? So basically these two things are same. So here again I will copy this because I will apply this operation because both of them are invertible. So this is contradicting, right? And if I make them side by side, like I'm applying the same thing because all of them are valid, right? Because both of them are invertible. So let me just okay, why is this taking so much of space? Yeah, here. Okay, fine. So like both of them are contradicting. Obviously this D option also won't be correct. Okay, D option also won't be correct. So here D is not correct. So what is correct? So obviously only one option is remaining. So C will be obviously correct here. But why is it correct? Why is it correct? Because it is correct because where x and y equals to 0. Okay, x and y equals to 0, but I will not be able to take the inverse of any of these two, right? So I won't be able to prove anything that either my x is null matrix or y is not null matrix. Sorry, this is not equal to 0, this is equals to 0. So obviously if it is equal to 0, that means these are non-invertible. Non-invertible. Okay, these are non-invertible. So like this is the obviously correct option. So C is correct over here. Okay, C is correct. But let's take an example, and from there we shall understand. Okay, so obviously we have to take an example such that the determinant of both of the matrices are 0 and their product is a null matrix. So just let us understand through an example. Okay, so let me take any random matrix which is, let's say, is 1 2 2 4. So here 1 2 2 4, row 2 is twice of row 1. This is, let's name this as x, and let me take another matrix which is x y w x y z. I can name this as w x y z, x y z. Okay, and let me name this as y matrix, and the product of these two should be a null matrix. Okay, so if it is a null matrix, so definitely what I can write from here, the relationships, that is w plus 2y equals to 0, x plus 2z equals to 0. Okay, and these two equations I have. So basically, like I have infinite solutions over here, so whatever value I choose, so let me choose a value, let w equals to 1, then your y has to be sorry, let me choose w equals to 2. W equals to 2, then your y has to be minus 1, and let x equals to 2, then z has to be minus 2. Sorry, z has to be minus 1. Okay, so yeah, let me just put this up and like back calculate that whether this is equals to null matrix or not. One two two four, and then we have this w I have chosen as 2, and y as and z as minus 1, y and z at w x y z as minus 1. Okay, so let us multiply these two matrices. So this is equals to 1 times 2, 2 times minus 2, so 2 minus 2 is 0, then again 1 times 2 minus 2, so this is also 2 minus 2, this 2 times 2 4 minus 4, so 4 minus 4, this is 2 minus 2, 2 into 2 into minus 4, so which is 4 minus 4, 0. Okay, so yeah, this is basically the answer to this question. Let's like you got to see, right? So here the determinant of these two are 0, but they are not null matrices, right? They are not null matrices. So then also I am getting my product as null. Okay, so basically what is the key point here? The key point is this, right? If they have given you that the product of two matrices is equals to a null matrix, then there can be three things. Okay, three things: either both of them are null matrices. Okay, if both of them are null matrices, anyways the result will be null matrix. If either one of them is null matrix, it doesn't matter what the other matrix is, obviously the product will be null matrix, because 0 times anything is 0. Here also 0 times anything is 0. Then here, if both of them are in null matrix, then what will happen? If both of them are in null matrix, then what will happen is both A and B have to be singular matrices. Basically, inverse should not exist. Sorry for burping. Inverse should not exist, and their determinant should be equals to 0. So this is valid only if the third case is valid only if A and B are singular. Okay, A and B are singular, hence determinant of A equals to 0, 0, determinant of B equals to 0. Okay, that is basically both matrix A and B are not invertible. So yeah, so this is the total summary of this. So obviously let's go to the question which lecture. Basically, obviously we have already like used up 25 minutes. So let me try to solve these quickly. So I will go through this quickly because you already know this during 11th and 12th, and if you know, you can skip, like go into X or something. Okay, just I will try to give few important points over here. So what is a symmetric matrix? A symmetric matrix is a matrix in linear algebra which is a square matrix. So very important, this is a square matrix. Just hold on a second. Yeah, it is a square matrix that remains unaltered when its transpose is calculated. Basically, E equals to A transpose, right? So transpose we have already learned, I think, right? Transpose I have already taught you. Yeah, sorry, the connection got cut basically. So I was telling that transpose, I have already told you what is transpose. Transpose means basically rows are interchanged into columns. So here the definition is also given, where Aij equals to Aji for all I comma j. Okay, for all I comma j. Okay, what does this mean? So basically, let's take an example. Let me take A equals to 1 3 3 2. Okay, here what do you see? If you take the transpose of this, what do you get? So let me take 3 examples and tell me which of them are symmetric matrices and which of them aren't symmetric matrices. Okay, 1 2 3 2. Okay, so let me take the transpose of this and you can like think which of them are and aren't symmetric matrices. A transpose equals to okay. So here what is the case here? So here what do you see, that these two are equal, so hence this is a symmetric matrix. This is a symmetric matrix. Again these two are equal, so hence this is also a symmetric matrix. Are these two equal? No, these two aren't equal, right? These two aren't equal. Okay, here this is 2 2 and here this is 3 2 and here this is, so these two aren't equal, so this is not a symmetric matrix. Okay, so this is how you understand A equals to A transpose is a symmetric matrix. Or you can further write this. Okay, you can further rewrite this as A minus A transpose equals to 0. Okay, you can take this A transpose on the LHS. So this is A minus A transpose equal to 0. This is also equation. Now one more interesting fact I want to tell is how many non-trivial elements are here. Basically, how many non-repeated elements are present. So I will write, just hold on a second. Non-trivial means non-repeated. Basically, important elements. Trivial means unimportant, but non-trivial means important elements which are non-repeated. So in this case, if we check, non-trivial elements here are 3. Like here 1 is a element, 2 is a element, 3 is element, but this 3 is again repeated. So I will only choose one of these. So how many unique elements I have? Unique, or you can say unique. Okay, so in this case, for let me name this as case 1, case 2, because I have 2 symmetric matrices only. So for case 1 I have 3 non-trivial elements. Three non-trivial elements. In the case 2, how many do I have? I have only one, because how many unique elements I have? Only one, because it's always repeating one. Okay, so obviously I have only one non-trivial element. Okay, one non-trivial element. So basically now I want to like give you the properties of symmetric matrix, and in there is a thing about non-trivial elements. So first is, if A A matrix is a symmetric matrix, then A raised to power k will also be symmetric. A raised to A inverse is also symmetric. A transpose will also be symmetric. Adjoint of A will also be symmetric. A plus A transpose will also be symmetric. A transpose plus A will also be symmetric. You derive for yourself and you will be able to understand. And obviously get the intuition why are they symmetric. That also you try to get the intuition. Okay, so basically how you can say. So this A raised to power k, right? I'll just give you a brief. A raised to power k, I'm just doing this in rough. A raised to power k, let's say A raised to power k is some matrix B, or let me do it for A square. A square. A square is some matrix B, okay? It's a matrix B. So what I can write A square as A times A, right, equals to B. Now what I'll do, I will take the B transpose of this whole thing. So if I take the B transpose of the whole thing, this will get swapped and individually they will get, basically I'm taking the transpose of this whole thing. So obviously A gets swapped and you're not able to see because they are same matrices, and individually I will take the transpose. Now what is A transpose? A transpose is equals to A because A is a symmetric matrix. So this will be equals to A times A, which is equals to A square. So which is equals to my B. So my B transpose equals to A, and like this you can prove for all other matrices, like all other powers. Okay, so this is the basic intuition. A inverse also you can do it like that. A transpose is already symmetry because A transpose is equals to A itself, and yeah, all this you can do, right? So next is maximum number of non-trivial elements in a n cross n symmetric matrix. So how many maximum number of non-trivial elements, unique elements can I have in a symmetric matrix? So how many can we have? So basically the diagonal, right? This diagonal can be any number. Okay, they don't have any condition. Okay, this is about only the non-diagonal elements. I, j and ji are only about the non-diagonal elements where I is not equal to j. Okay, so in this case I should have written it. I is not equal to j. I don't have space. That is very unfortunate. I is not equal to j. Okay, so I is not equal to j. So this is the case. Now basically the diagonal elements don't have a foundation, so they can be anything. So let's assume that they are all unique. Okay, now how many total number of elements can a n cross n matrix have? N cross n means what? The size of the array. Okay, n times n rows, n columns, which means n square elements I have. Or just simple understand this, 2 cross 2, how many elements I have? 4. 2 times 2 is 4. 3 cross 3, how many elements I have? 9. 3 and 3, 9. So 3 square. So n cross n square. So how can we derive this? So basically I will write this statement later, talk about this statement later. So total elements equals to n cross n equals to n square. Okay, and how many diagonal elements I have? So basically for a 2 cross 2 matrix, how many diagonal elements will be there? I equal to j, basically 2 diagonal elements. For 3 cross 3, 3 diagonal elements will be there. For 4 cross 4, 4 diagonal elements will be there. So for n cross n, n diagonal elements will be there. N diagonal elements. Okay, n. So just hold on a second. And what is another thing? Another thing is that how many non-diagonal elements I have. Basically, which is simply subtract the total number of elements with diagonal elements, you will get non-diagonal elements. But can you tell me how many elements are above this diagonal, main diagonal, and below this main diagonal? Can you tell me the number with respect to n? Okay, can you tell me the relationship? Basically, half will be divided at the top and half will be divided at the bottom. Symmetry, right? Symmetry. For 3 cross 3, half will be in the bottom and half will be in the top. For 3 cross 3, basically it is 2, 3 in the top and 3 in the bottom. For up here, it is 1 in the top and 1 in the bottom. So basically, non-diagonal elements. Color this. So why am I deriving this? Because this may come in handy in some other way, right? Some other way this may come in handy. That's why I'm deriving this. Else I would have simply told you the formula and just remember it formula. Okay. So but I generally I myself don't remember the formula. That's why I don't you to also remember the formula. Okay. So this will be n square minus n. Okay. Now above the diagonal elements and below. So basically I will divide this in 2. Okay, divide by 2. n. Now I will take common n minus 1 by 2. Okay, now this is basically half will get divided. Basically above the diagonal, above the principal diagonal and below the principal diagonal, these are the number of elements. You put n equals 2 over here. If you put n equals 2, you will get 1. You put n equals to 3, what you will get? 3 into 2 divided by 2, which is 3 itself. So three elements are above the principal diagonal and 3 elements are below the principal diagonal, which is correct. Simply it is dividing into half. That's why I divided it into half here. So now they are talking us about the maximum number of non-trivial elements. So what can be the maximum number of non-trivial elements? The maximum number of non-trivial elements can be, obviously all diagonal elements can be unique, okay, and the either the bottom half and the top half, all of them can be unique, but the other half has to be same as this other half, right? Basically if this is 3, this has to be 3 for it to be a symmetric matrix. So basically whatever is the below of the diagonal, principal diagonal, it has to replicate the above the diagonal, principal diagonal, right? The elements have to replicate them, whatever, vice versa. Okay, you can talk about that. So basically what we have to say is maximum number of unique elements here can be n into n minus 1 divided by 2. One half can be unique. So one half can be unique over here. One half can be unique. Okay, so now one half is unique and the total all the diagonal elements are unique. So total number of non-trivial elements is basically equals to this diagonal elements plus n square minus n divided by 2. Okay, now if I add this n, this will become n square plus n divided by 2, which will be n into n plus 1 divided by 2. So this is where from where we derive the formula, right? Why I showed you, because someday they may ask you something different, okay, not about unique elements, something different. So then you have to go with the basic derivation itself, or you can simply put the value of n in the options if they have given you in the equation format. So you just put the value of n like 3, 2, and from there you can do manual calculation, okay. But if you don't have that option, then you have to derive it. So this is how you derive it. So here we get n into n plus 1 by 2, which is written over here. So maximum number of non-trivial elements that we can get is n into n plus 1 divided by 2. Okay, also this is another point which I will talk about in the eigenvalue section. We haven't even learned eigenvalues, but just I want to give you like the properties. So I have to tell you this, that the eigenvalues of symmetric matrix are always real and positive. If you don't know, don't worry, this will come in handy while you are revising the subject. Eigenvalues will learn. Okay, next is skew symmetric matrix. Okay, it's almost same only, it is also a square matrix. Okay, but here the difference is it is a negative of its transpose. Here previously it was equal to its transpose, now it is negative of its transpose here, as you can see. So aij will be equal to 0. Basically when it is diagonal elements, the diagonal elements will be equal to 0. Okay, because 0 equals to minus 0, only then it is possible. That's why the diagonal elements has to be 0. Okay, and all other elements has to be the negative of them, like above the diagonal element and the below the diagonal element. Okay, so let me do a few examples and from there we'll understand. So let me take a few examples, like a equals to 0, 0, minus 3, 3, then equals to 1, 2, minus 2, 2, equals to 0, 0, 3, 3. Okay, so just taking basic examples. So here if I do the A transpose, what do I observe? I observe that this is 0, 0, 3, minus 3. This is 1, 2, diagonal elements won't change, this will be 2, minus 2, and this is 0, 0, 3, 3. So what do you observe? Here we observe that a is equals to minus a. A is equals to minus a, because if I multiply a minus 1 with this will become plus 3 and this will become minus 3, which is simply equals to the a, right? So sorry, a is equals to the minus a transpose. So this is a uh, this is a skew symmetric matrix. Okay, so then what about this? What about this? So here what we are observing, yes, the non-diagonal elements are following this relationship, but the diagonal elements aren't. That's why they can't be zero. If it is equals to, if it is not equal to zero, then if I multiply -1, this will be -1, this will be -2, this will be 2, this will be -2. These elements are equal, but these diagonal elements are not equal anymore. Hence, they can't be a non-zero value. They have to be zero. Hence, this is not a skew symmetric matrix. This is also not a skew symmetric matrix. This is a symmetric matrix. Okay, so yeah, this is the case. Now let's do one thing, like let's further extend this. What I can extend, A plus A transpose, right, equals to the null matrix. A plus A transpose equals to the null matrix for a skew symmetric. If it follows a skew symmetric relationship, it will be equals to the null matrix. Okay, so yeah, let's understand few properties about this. The principal diagonal element of a skew symmetric matrix is always 0. The summation of all the elements will be equal to 0. Why? Because this is negation of this, and obviously the diagonal elements are 0. So all the sum will be 0. Okay, simple thing. If A is a skew symmetric matrix, then A raised to power 2n and A raised to power 2n plus 1 will be symmetric and skew symmetric matrix. Okay, so you just check for yourself that what is n, is any positive integer here, n is any positive integer. So if I take the power of a matrix, any even power of a matrix, then it will be a symmetric matrix. Okay, you can cross verify, you can check for yourself. So I will obviously do an example, and from there we'll check. And if you take the odd power of any skew symmetric matrix, it will always be a skew symmetric matrix. If you take the even power, it will always be a symmetric. If you take the odd power, it will always be a skew symmetric. How do you remember it? So you can remember that A equals to minus A transpose. If I do A square, it will be minus square, it will be positive. So it will be equals to the positive. So if it is positive, then again it will follow the A equals to the plus A transpose, like that. It is just an analogy. Okay, it is just an analogy. Now if you do cube, A cube equals to the A equals to the minus A transpose. If I do the cube, -1 cube is -1. So it is A equals to the -1 A transpose. Hence it is a skew symmetric matrix. Like negation is still there, right? And if I do square, negation is gone, it becomes positive. Hence it is a symmetric matrix. So this is how you can remember this. So let's take an example, and from there we can understand. So like we have a matrix, and this is skew symmetric. We have to find the determinant. We have to find the A square. We have to find the A cube. Okay, so first let us find the determinant. So if we find the determinant, this will be 0 plus 9, which is 9 itself. Okay, so this is a perfect square. This I will come to in the next slide. This is a perfect square. Next, about the second thing, A square. So A square, don't just do this, that A square is this, right? This will be a blunder. Okay, this will be a blunder. You don't do this, right? Don't do this. What you do, like a few people make the mistake. So what you simply do is A square will be equals to the 0 minus 3 3 0 equals to 0 times, so this will be -9, this will be 0, and this will be 0, this will be 0, this will be 0, this will be -9. So here if you take the A transpose, this is a symmetric matrix, right? So if you take the A square transpose, this is equals to the A square itself. So because these two elements are equal to each other. Okay, so yeah, this is symmetric matrix. Hence, like it is proven that if you take the even power, it becomes symmetric. If I take the odd power, what will happen? If I take the odd power, basically I will do the A cube, which is equals to the a square into a. Okay, so what is a square? A square is this minus 9 0 0 minus 9, and this is equals to the 0 minus 3 3 0. Zero, this will become 0 itself, and this will be 27, and this will be minus 27, and this will be again 0. So what do we observe here? Well, we observe that your a cube is simply equals to the a cube whole transpose, right? Not simply equals, there is a negation sign also. Negation sign also. Okay. So yeah, this is what this becomes. Okay, so hence this is a skew symmetric matrix. So like it is proven that whatever it was written, that odd power skew symmetric, even power symmetric. Okay, now if A is skew symmetric matrix, then if n is even, then your determinant won't be equals to 0, it will be a perfect square. Okay, and if n is odd, then determinant will be equals to 0. So you just check the determinant of this. So what do you mean by this? So yeah, basically the order here, in this case the order was 2 cross 2, so n was even, hence the determinant was a perfect square. You take any skew symmetric matrix of order odd order, it will be, determinant will be 0. Okay, and in this case also obviously the inverse will exist, right? Inverse will exist because determinant is non-zero. Here in determinant is 0, inverse won't exist. So if inverse exists, then it will follow skew symmetricity. Basically for even order, the inverse will also be a skew symmetric matrix. Okay, A inverse, let me finish this quickly, will skew symmetric matrix. Okay, so now like what is the maximum number of non-trivial elements? So this time how many non-trivial elements can be there? So basically maximum non-trivial elements can be in this area, right? Either in this area or like this area, because these are not unique, these are zero only, and these are only unique because one half is unique, because other half is negative. Okay, okay, so then we tell them as, because this is negative of this, then we tell them that if you know this, you can simply find this, right? Hence they are followed by a relationship, hence we don't count them as unique. So in this case the maximum non-trivial element was only 1. Okay, because why is here, because why is this a case? Because for a skew symmetric, this information is already known that the diagonal elements will always be 0. If it is a skew symmetric matrix, we already know that diagonal elements will be 0. We don't need to know anything new about this, that is already known for a skew symmetric matrix. For a skew symmetric matrix, basically diagonal elements will be 0. This is already known. Okay, what is the other thing known? What is known is basically the non-diagonal elements. If you know the one half of non-diagonal elements, the other half will be the negation of it. So elements above principal diagonal here equals to basically negation of elements below principal diagonal. Okay, elements below principal diagonal. Elements above principal diagonal is equals to the elements below principal diagonal. Okay, so if you know this, then obviously we know this. Okay, so only these are non-trivial, all these are trivial because we already know about all this information, right? So basically what I can write is, like, what was this? Elements above principal diagonal was this only. Okay, elements of principal, number of elements above principal diagonal was this only. We already derived it previously here. We've already derived it, right? 1/2. So I will copy this, I will just copy this, I will paste this thing over here. Elements above principal diagonal. Okay, okay, so this is the case. I have got the like reasoning behind this. Why is this equals to n into n minus 1? Next is this. So any matrix A can be written in the format of A plus A transpose by 2 plus A plus A transpose A minus A transpose by 2. So if you break this down, this will be A by 2 plus A by 2, which is A only, and this will be A transpose by 2 minus A transpose by 2, which will be cancel out. So it will go stay. But what is the interesting fact is that A plus A transpose is equals to what? A plus A transpose is equals to the asymmetric matrix that I've already written in the properties section. So this is equals to a symmetric matrix and A minus A transpose is equals to the skew symmetric matrix. So basically what do I want to say over here is that any matrix can be written as a summation of symmetric and skew symmetric matrix. Any matrix, okay, it can be written as a summation of symmetric and skew symmetric matrix. But what is the condition? Condition is it has to be a square matrix. It has to be a square matrix. Okay, so if it is a square matrix, then it can be written as a summation of symmetric and skew symmetric matrices. So basically another like note about eigenvalues is that eigenvalues of a skew symmetric matrix are either 0 or purely imaginary. Okay, we'll understand this when we study about the eigenvectors and eigenvalues. Okay, so now let's study about the orthogonal matrix. This is a very important matrix. So basically a orthogonal matrix is a square matrix. Again, this is a square matrix also. Please do take a note whichever are square matrix. I'll try to summarize. Okay, I'll try to summarize obviously, but you also take a note. So it's a square matrix A if and only if its transpose is same as its inverse. So here it is written, right? If I take the transpose of it, it should be equals to its inverse, right? It should be equals to its inverse. So why is it the case? Why is it the case? So basically what does orthogonal mean? Orthogonal means perpendicular. If you have written that these two vectors are orthogonal to each other, these two vectors are mutually perpendicular to each other. So orthogonal means perpendicular, which I will show you visually. What do I mean by this? Okay, we'll see this visually, but for now understand this is perpendicular. Now further, like, this is the main definition. Okay, further I can write results from this, and this is mostly what is used in our case, which is equals to that if I pre-multiply and post-multiply, if I post-multiply A on both sides, this will be A transpose times A equals to I. Okay, because I am post-multiplying. Now I don't want to write I over here, this I will be here. Okay, and if I pre-multiply with A, this will be simply A into A transpose. Okay, so this I is of order n. So like you are seeing that if I multiply the transpose of that same matrix, then I should get a identity matrix. So this is also an important information, because through this only we will be able to prove that whether this matrix is a orthogonal matrix or non-orthogonal matrix. Okay, orthogonal matrix or non-orthogonal matrix. So what are the conditions? Okay, the condition for a matrix to be orthogonal is that a square matrix is orthogonal if its inverse is equal to transpose. That is already known. If A is orthogonal, then A and A transpose are inverses of each other. Okay, that is A and A transpose are inverses of each other. Yeah, A and A transpose are inverses of each other, which is true again. The determinant of an orthogonal matrix is either 1 or minus 1. So if a matrix is orthogonal, then its determinant will be 1 or minus 1. Also, the dot product of any two rows of an orthogonal matrix is always 0. Okay, we understand this point. Again, any row slash column of an orthogonal matrix is a unit vector. So basically, these 2 points combined telling us that rows and columns, any two rows and or any two rows slash columns are orthonormal. To each other. Okay, these 2 conditions mean these, that they are orthonormal. Basically, ortho means perpendicular, normal means unit vector. Okay, unit vector. So let's understand this. What do you mean by orthogonal, and what do you mean by orthonormal and unit length? So let us say that we have a matrix A in this like this. That this is, I'm talking about columns now. You can do this with rows also. Okay, any whichever example you take, columns and rows. Okay, and this will be A1 I. Now what I can write? I can write this column as a vector. We'll obviously study more about vectors later on, but for now you can understand that I can write this whole column as a vector. I already showed you, right, during solving with the vector representation, that I can write a column as a vector. So A1, I can write this as A1 I cap plus A2 j cap, and I can write this as B1 I cap plus B2 j cap. Okay, B1 plus B2 j cap. I can write these two. Now, what does orthogonal mean? What does orthogonal mean? So to satisfy orthogonality means that these two, dot product of these two has to be equals to 0. We have studied this, right, in vector algebra during class 11-12. If you haven't already, then don't worry. When we'll study about the vector calculus, there I will teach you all this. Just for now, try to understand that dot product of these two vectors, like let me name this as C1 vector and let me name this as C2 vector. So C1 dot C2 has to be equal to 0 because they are orthogonal to each other. They are perpendicular to each other. Okay. So basically, I can write this A1 I cap plus A2 j cap into B1 I cap plus B2 j cap equal to 0. Okay. So this is A1 B1 plus A2 B2, because I dot I, we will only do I dot I, right, and I dot j is simply equals to 0 itself, right? I dot j is simply equals to 0 because it is what basically it is cos 90. I dot j is 1 times 1 magnitude of I into magnitude of j, which is 1 times 1 into cos 90. Cos 90 is 0. That's why. So this is a1 a2 should be equals to 0. So this is the condition that they need to satisfy for it to be orthogonal. Now I have to check for rows as well. So row vector, let me just use this colors over here. Now I have to write in terms of rows as well. So rows I can write this one, this is a row and this is also another row. So this, let me name this as first row. So row 1 equals to a1 I cap. Again I am writing with I and j. These are basically basis vectors. What is a basis vector? Also we'll understand in the this vector topic which will come in the next few lectures. So don't worry. So these are basically basis vectors. A1, B1, j cap, and my row 2 equals to a2 I cap plus b2 j cap. Okay, so basically this will be simply what I can write is again r1 r2 dot should be equals to 0. So if these are equals to 0, then this means that e1, I will copy these two rows basically. Has to be equal to 0. That means that this relationship has to be followed, that is a1 b2 plus b1 a2 equals to 0. So these two relationship has to be followed. Now what is the other thing? What is about the unit length, unit vector? So what do you mean by unit vector? Unit vector, if you know already, well and good. If you don't know, basically the determinant of c1, so not a determinant, the magnitude of c1, like I'm accustomed to speaking determinant, that's why. So magnitude of c2, magnitude of r1, magnitude of r2, okay, any rows or column, okay, these vectors, they have to equal to 1. They are unit vector. Unit means 1, okay, all of them, the magnitude has to be equal to 1. So what is the magnitude formula? So basically determinant of magnitude of c1 is under root a1 square plus a2 square, a1 square square plus a2 square, okay. Then magnitude of c2 equals to this, what is it? It is b1 square plus b2 square, okay. So which is equals to 1 itself, Now if you square both sides, basically a1 square plus a2 square equals to 1, which most probably tell you this, but like first obviously under root is there, and if you square it, so only 1 square is 1 itself, so it doesn't change anything. So like the same thing will happen, like my r1 square, like magnitude of r1 will be a1 square plus b1 square, is it? Yeah, a1 square plus b1 square should be equals to 1, and magnitude of r2 should be equals to a2 square plus bt square. Now obviously you don't have to check all of this, okay. Either, what is the point here? You don't have to check all, like row or like every time row, column, all of this. Either check row, either check all rows or all columns. You don't have to check two of them simultaneously, okay. Either check all rows or all columns, okay. So this is the first thing. So basically like you can you can see it for the 3 cos 3 also. I will not show you, okay, but let's visually understand how a matrix is orthogonal and what do you mean by orthogonality. So here Let me take an example, very simple example, which is a identity matrix, which is also a orthogonal matrix. 0 1 0 0 0 1. Does it follow the principle? So basically it's A transpose has to be equals to A inverse. A transpose has to be equals to A inverse. Okay, so basically what is the A transpose? The transpose of orthogonal the identity matrix is identity matrix itself. So A transpose is same only, which is equals to the identity matrix itself, and A inverse, the inverse of identity matrix is identity matrix itself, because one inverse is one itself. So A inverse is also this, right? Identity matrix. So basically what I can say A transpose equals to A inverse. So now let me draw the axes. So basically let me draw three axes, because this is a three-dimensional matrix, I mean 3x3 matrix. So this is I, this is J, this is K. Okay, this is K, right? So what do you mean by orthogonality? Basically they are all, what do you mean by basis vectors? They are all 90 degree apart. Okay, they are mutually perpendicular to each other. We will obviously study about basis vector. For now you will understand that they are 90 degree apart, right? These are simple axes, 3D axes. You already know this, that the axes will be 90 degree apart. They are in I cap J cap direction. Now here what is my C1? So my C1 in this case is only I cap, right? Because 1 into I cap plus 0 into J cap plus 0 into K cap, and my C2 vector is J cap simply, and my C3 vector is K cap simply. Okay, so C1, C2, C3 is K cap simply. So this is the first thing. So can I plot my vectors in this axis? So this is my C1 vector, this is my C2 vector, and this is my C3 vector. What do you observe? What do you observe here? They are all mutually perpendicular to each other. Okay, and obviously their magnitude is 1, because 1 square plus 0 square plus 0 square is 1. 0 square plus 1 square plus 0 square is 1. Again, the next column is, it is also 1. So here we observe visually C1, C2 and C3 are mutually perpendicular to each other. Okay, are mutually perpendicular to each other. So visually you can understand like this. So let's do a question on this, that you have to calculate the value of x if A is a orthogonal matrix. So if A is a orthogonal matrix, you have to value the calculate of x. So basically method 1 is very simple. We know already A is a orthogonal matrix. You just simply use that dot product or the unit vector formula. Okay, unit vector property. So here method 1, is simply use that property. Method 1 is, so let me just, either you can go row wise or column wise, it doesn't matter. Okay, I'm going row wise, whichever you are suitable. So row 1 magnitude should be equals to under root 12 by 13 whole square plus x square should be equals to 1 itself. Here you can cross verify that here 5 by 13 whole square plus 12 by 13 whole square is 1 itself, right? So yeah, it is satisfying this condition. Now this has to also satisfy this condition. It has to be unit vector. So from here, if you solve this, you will get that your x is plus minus, just not plus, it is plus minus 5 by 13. Okay, it is plus minus 5 by 13 because you're taking the under root as well, so you have to be careful with that. So now which one should I take? Which should I take, the positive one or negative one? So this you can eliminate by the next property, that is the dot product should be 0. So we will do the dot product between the each two of the rows. 12 by 13 into 5 by 13 plus x into 12 by 13 should be equals to orthogonal, should be equals to 0. So basically x equals to minus 5 by 13. Okay, you could have directly done this, but yeah, just to show you a few things, I did this slowly. So x equals to minus 5 by 13, or what you can do, or use this A transpose equals to the A inverse. Okay, so what is A transpose? A transpose is 12 by 13, this is x, this is 5 by 13, this is again 12 by 13. Okay, and this is equals to A inverse. So what is A inverse? Simply you, what do you do? You take the negation of this and you swipe these two principal diagonal elements. So these are same only. So these will be 12 by 13 only, 12 by 13 only, and you do the negation of this minus x, and this is minus 5 by 13. Now what is the determinant? So the determinant is either plus minus 1 with orthogonal. So let's check what is the determinant here. So it is simply, we don't know, but it is simply 12 by 12 by 13 whole square minus, so this is simply equals to 12, just hold on a second, 12 by 13 whole square minus 5x by 13. So what I can do is I can write in this format, this will be here and this will be here. Okay, this is 1. Now how do we derive this? So here what do we observe? If you multiply this with this, and this has to be equals to 12 by 3, so this has to be equals to what? This has to be equals to 1 here, this has to be equals to 1. From there also you can understand, or okay, so basically this has to satisfy, right? So if this has to satisfy, obviously what is this? Yeah, 12 by 3, right? So I will copy this. So this is scalar multiplied with a matrix, so it will get multiplied with all of the individual elements. So this is 12 by 13 should be equals to 12 by 13 itself. Okay, so this one is getting cancelled. So this one is getting cancelled. So my 5x equals to 12. Oh, just hold on a second. Yeah, this is getting cancelled. This is equals to this. Whole square. Okay, something is going wrong. Yeah, sorry for the mistake. Basically I just did one silly mistake, that's why you should not skip steps. So this one is equals to 12 by 13 whole square minus 5x by 13. So your x will be equals to this will go over there. Now this is 144 by 169, so minus 25 by 169, and here we have 5x by 13. So x will be equals to minus 5 by 13. Like from here also you can solve it, bit lengthy, but from here also you can solve it. Okay, or you can equate these. Okay, whichever is suitable to you. So this is how you solve this question. Okay, with method 1 and method 2. This is with the definition of orthogonal matrix. So what is next matrix? Next matrix is nilpotent matrix. So nilpotent matrix is a square matrix such that the product of the matrix itself is equal to a null matrix. So if I multiply the matrix with itself k times, where k is the index or exponent of the matrix, it will be equals to null matrix. Now null matrix is different. Null matrix means 0. Okay, but a may or may not be null matrix. Okay, so here A matrix may or may not be null. Okay, it's not necessary that A has to be null matrix. It is not necessary, but just hold on a second. But A raised to power k is a null matrix. So if you multiply A 2 times, 3 times, it will be a null matrix. Okay, so like let's take an example. Okay, so on the top of my head, like I've already written some matrix down, so it is 2 minus 2 minus 2. Now this is a very simple matrix. So basically what you do A square. So I will write this as equals to A. Now if I do A square, this will be 2 minus 2 2 minus 2 2 minus 2 2 minus 2. So this will be simply equals to 2 times 2 4 and minus 2 times minus 2, which is minus 4, then minus 4 and then plus 4 4 minus 4 minus 4 plus 4. So this is basically equals to null matrix. So I'm just writing, really sorry for my handwriting. So this is like 0 0 0 0, which is a null matrix. So here A is a nilpotent. A is a nilpotent matrix of index 2. So what are the properties of nilpotent matrix? So basically the properties are, a nilpotent matrix is a square matrix of order n cross n. Okay, so it has to be also a square matrix. It's very important. So I may have, yeah, I have written it is also a square matrix. So whatever we have discussed till now is our square matrix. So and next also whatever we will discuss will also be a square matrix. So yeah, it is a square matrix of order n cross 1. The index of nilpotent matrix having an order n cross 1 is either n or value lesser than n. So its index always will be equal to n or lesser than n. So here it is 2 cross 2, right? So it's if it is a nilpotent matrix, its index has to be equal to 2 or lesser than 2. Okay, that is also a very important property about the nilpotent matrix. All the eigenvalues of nilpotent matrix are 0. We'll learn about this later. The determinant or trace of the nilpotent matrix is always 0. Okay, why? From here you can derive, right? A square equals to 0, then you take the determinant on both sides. This is equals to 0, and A square, determinant of A square is equal to 0. So the determinant of A will also be equals to 0. Okay, so the nilpotent matrix is a scalar matrix. So basically here, if you take 2 common, it will be 1 minus 1 1 minus. So it's like a scalar matrix, right? That's why it is talking about the scalar matrix. And nilpotent matrix is non-invertible. Why? Because obviously determinant is 0, then obviously inverse won't exist. Okay, so next is a idempotent matrix. So again, idempotent matrix is a square matrix. There are a lot of matrices we need to learn, which when multiplied by itself gives back the same matrix. So basically A square equals to A. So that is a simple relationship about the idempotent matrix. The idempotent matrix is a square matrix. As I told, that idempotent matrix has an equal number of rows and columns. Okay, why is this the case? So it is a square matrix, that we already know. So this is like, why have I written it as a property? If we already know it is a square matrix, sense I should okay, what happened here? Oh, I came back to nilpotent. My tab is nowadays getting really hang right now. Okay, so this is like some property, just keep this in mind. And the idempotent matrix is a singular matrix. So basically here also it is determinant is 0. How? Like what do? You take the determinant on both sides. If you take the determinant on both sides, it will be a, okay, there is something wrong with this, sorry. It is not a singular matrix actually. Its determinant can either be 0 or 1. So it is not like, we can't always comment that it will be a singular matrix. So this property is also wrong. Okay, the non-diagonal elements can be non-zero elements. Like these are all weird way like I haven't noticed. Like whatever properties I've found out I've tried to include. Okay, these are also very bad. So the eigenvalues is either 0 or 1. We'll talk about this later. The trace of an idempotent matrix is equal to rank of the matrix. We'll also learn about this. The trace we already know, right? And the trace of an idempotent matrix is always an integer. Okay, so like okay, like I am not taking example, we don't have enough time anymore. So basically what you can say, like, let me take a 2 cross 2 matrix, and from there we'll understand the example. So example, let me take a b c d square. Okay, so basically a b c d square will be a b c d a square plus bc ab plus bd. Yeah, then this is ac plus dc bc plus d square, which has to be equal to like a itself, because a square equals to a, right? A square equals to a. So a b c d. So from here, what relationship can I get? So this will be a square plus bc equals to a. Okay, then this can be written as a into 1 minus a equals to bc. Then this e plus t into b equals to b, hence a plus d equals to 1. So this is one relationship. And next is this ac. So c into a plus, okay, we get back the same relationship equals to 1 itself, so we don't need to write this. So from here, like, either b can be 0, right? B can also be 0. So from here, b, either two things can happen: either b is equal to 0, okay, or a plus d equals to 1. Two things can happen, and b is not equal to 0. Okay, what is next? Next is bc plus d square equals to d. So again, bc plus d square equals to d. So what I can write, d into d minus 1 equals to bc. So these two are same only. So what I can write is a into 1 minus a equals to d into d minus 1. Okay, so basically if I choose a as 2, okay, what will happen if I choose a as 2? Let's say a is equals to 2. So if a is equals to 2, then from here what we get, here we get d is equals to minus 1. So if minus 1 is satisfying, no, minus 1 is not satisfying. Okay, that is not possible. So if a is equals to 1, if a is equals to 1, then d is equals to 0. Okay, these two are satisfying. So if a is equals to 1, d is equals to 0, this is satisfying. A is equals to 1 and d is equals to 0. Okay, so yeah, this will satisfy. So this is satisfying. Now if, so what will be b times c? B times c will be simply 0. So either c has to be 0 or b has to be 0. B can't be equal to 0, so c has to be 0. So c equals to 0. Okay, so if c equals to 0, then I think b can be any value. B can be, okay, can be, no, b can't be any value. So basically, no, this is okay. Yeah, b can be any value. B can be anything. So let me take b as 2, and let's check whether this matrix is idempotent or not. So here this is 1 2 0 and 0. Okay, so determinant of this is 0, that is one thing. So this is a singular matrix. Okay, that is true. Next is, let me multiply it with this. So 1 square 1 2, then this is 0 and this is 0 also. Okay, so 1 times 0, 1 times 0, and this is 0 times 0, this is 0 times 0. Okay, so 1 2 0 0. Okay, so yeah, here we can see that this is an idempotent matrix, and in this case the trace is an integer number. Okay, trace is integer, which is 1 right now. Okay, the rank we'll talk about later. The eigenvalues are 0 or 1. Yeah, the eigenvalues are 0 and 1. That is correct. Okay, because it is like a diagonal like upper triangular matrix, so it will be this and 1 and 0. We'll talk about this later. Okay, and about the determinant case, the determinant can be two things here. So here what we can see, if you take the determinant of this, right, if you take the determinant of this, so basically determinant of a square equals to determinant of a. It is simply a square determinant equals to determinant of a. Now here two things can happen, right? Here what can happen, determinant of a can come on the left side, and I can take determinant of a common, and minus 1 equals to 0. So either determinant of a is equals to 1 or determinant of a equals to 0, right? These two things can happen. So determinant of a can be 1 also. I will have to check this in the next lecture. I will have to cross verify whether like this condition is correct or not. I will have to cross verify, right? So I forgot to cross verify this. I will have to cross verify in the next lecture. And what is the next matrix? The next matrix is involuntary matrix. Involuntary matrix and matrix is a special kind of matrix as it satisfies the self inverse function. That is, an involuntary matrix is its own inverse. Basically a equals to a inverse, right? And we can write like a square equals to I, right? A square equals to I. So this is the relationship about the involuntary matrix. So let's see the properties. A and B are involuntary such that matrix AB equals to BA, then AB is also called a involuntary. How is this the case? So basically, if A and B are involuntary, right? So A and B are involuntary, that means A is equals to A inverse and B is equals to B inverse, right? So now AB has to be equals to BA. So if AB is equals to BA, then AB is also an involuntary. So what is AB? AB I can write A inverse and B inverse. Okay, and what is BA? BA I can write B inverse and A inverse, right? So now let me name this. So let me take the whole inverse of this. So basically AB is equals to BA, that we know. Then AB is a involuntary matrix. So let me take the whole inverse of this. If I take the whole inverse, what will happen? If I take the whole inverse, just let me take this here. AB whole inverse is B inverse A inverse. Now what is B inverse A inverse equals to? B inverse A inverse equals to BA, right? B inverse A inverse equals to BA. And what is BA equals to? From this relationship, BA is equals to AB. BA is equals to AB. So AB inverse is AB. Okay, hence AB is also a involuntary matrix. Okay, hence AB is also is the spelling correct? Voluntary. Okay, my spelling is actually wrong. Involuntary. My spelling is wrong. It's not involuntary, it's involuntary. Okay, let's correct this. Here also let's correct this. Okay, so involuntary matrix. So let's read this. Eigenvalues of involuntary matrix are always plus minus 1. Like we don't know eigenvalues, so we will learn about this later. The determinant of any involuntary matrix is always plus minus 1. How can I tell this, right? So determinant of A square here, what I can write? This is determinant of A square equals to 1, because determinant of I is 1. Now if I take the under root of this, obviously if I take the under root of this will be equals to plus minus 1. This will be equals to plus minus 1. Okay, so determinant of A is plus minus 1. The involuntary matrix A is an idempotent matrix if and only if A is a identity matrix. if and only if A is identity matrix, then it will be also a idempotent matrix, because if A is identity matrix, I square equals to I itself. So this satisfy this condition also, and this satisfy I square equals to I. This satisfy also. Okay. So yeah, we got the example, right? So if A is a identity matrix, I forgot about this. So if A is an identity matrix, then determinant will be obviously 1, and it is also a idempotent matrix. Okay, so from here that whatever key point there was, it is a singular matrix, that is wrong. Okay, the determinant can be 1 as well for a idempotent matrix. So we just got the answer in our this lecture only. Okay, so another matrix is there. So okay, another thing about I wanted to tell you is that just hold on a second. If A is involuntary matrix, then let me write, if A is a involuntary matrix. Okay, if A is an involuntary matrix, then A square equals to I, right? A square equals to I, that we know. Now if I multiply A cube A with this on both, post multiply pre multiply A with this on both sides, so what will happen? A equals to A cube. Okay, so now just understand this is a odd power, right? This is a odd power. Okay, just we want to find a pattern over here. So now again I multiply A on both sides, this will be A square. So this will be what? This is a even power. This is a even power. And what is A square? A square equals to I itself. So I can write this as I. So even power will always be equals to I, and odd power will always be equals to like A itself, right? So basically what do you want to say is, now if this A cube, right, this A cube is also involuntary, this A raised to power 4 is also involuntary, because if I take the square of this will be A raised to power 8, which is equals to I. You can cross verify, which is equals to I. If I take the square of this A cube, it will be A raised to power 6, which is again equals to I, So basically if like A is involuntary, then A raised to power n is also involuntary, is I plus. Okay, so yeah, A raised to power n is also involuntary for n equals to I plus. So this is one condition I want to tell you. Next is about periodic matrix. So A square matrix where the number of rows and the number of columns are equal satisfy this relation. Basically A raised to A n cross n is a periodic matrix if A raised to power k plus 1 equals to A itself. Okay, so where k is a period. Basically there, what was the involuntary condition? If I do A square, it should be equals to A. Now here if I multiply A k times, then it should be equals to A itself, right? If I multiply A k times, then it should be equals to A itself. So where k is the period basically, so I am multiplying k times. Now if in this equation k is equals to 1, if you found out that k is equals to 1, that means my A is also involuntary matrix. Okay, A is also involuntary matrix. Okay, so basically I think this is it for this lecture, because we have still few types left. Okay, about the complex numbers, complex matrix are also left, so we'll do those complex matrix in the next lecture. Also we'll do questions on the next lecture, so next lecture will also be very interesting. So like if you already know all this stuff, you can obviously watch this in 2x, but don't skip anything, because it may so happen something important I'm talking about, because the derivations I'm doing, all these things, derivations you wouldn't have done previously, you would have just mugged up the properties, right? So I'm also trying to do the derivation so that you can understand the concept as well. Okay, so I hope you are liking the approach. So if you have any more doubts, you can ask in the Telegram group, or like in our doubt section, so or in the comments below. So I'll see you in the next lecture. Thank you for watching.